Hello everyone. So we have been discussing chemical kinetics. So let us begin our discussion or resume our discussion once again regarding that. Up to the last video, we had discussed about the rate of the chemical reaction. We had said at that point of time that it is the very first time that in a chapter the time is introduced related to the chemical reaction. Today, since we have to discuss further, we will try to understand that what are the factors on which rate of a reaction depends, what is an order of a reaction, what is the molecularity of a reaction, and most importantly, how the rate is expressed. So these are the things that is there in we have to discuss today. At the same point of time, as I have told you, that numericals are one of the key factors in this particular chapter. So we'll be discussing about numericals also. So each and everything will have a mathematical aspect. I expect you to go through this topic again and again, and obviously, as I have mentioned, the mathematical expressions and its physical significance has to be understood very carefully. So let us see what is there in store for us. Now, after knowing the rate of the reaction, today we are going to look into the experimental measurement of reaction rate. So experimental measurement. Experimental measurement. So here we need to look into, we have already said that rate means it is the concentration by time. So obviously we can do it graphically as well. In that case, what we used to do is, we can do this one. Suppose suppose a reaction we are choosing. Suppose we are choosing the reaction of N2O5 giving rise to 4NO2 plus O2. I think it is like this. So here obviously rate is depending on this one. So there can be a graph. First of all, there will be some experimented values. Okay. So here concentration of N2O5, you can say concentration of N2O5 versus time, and there will be some values, and obviously time will be measured in seconds. Time will be measured in seconds, and for N2O5 it will be moles per liter. So for this, suppose at 0, when the concentration, at the initial concentration of this, with time what happens? This concentration will decrease. So suppose this was 2.2 into 10 to the power minus 1. Then suppose after 10 seconds, it becomes 1.6 into 10 to the power minus 1. And suppose after 15 seconds, it becomes 1.1 into 10 to the power minus 1. And after say 30 seconds, it becomes 0.6 into 10 to the power minus 1, and so on. So usually what we do is, we have to draw a diagram or graph. So suppose, let's do that. So here the concentration, and on this side the time. This is drawn. Now, we are not doing it quantitatively, not to scale. Suppose this is the nature of the graph, suppose. Now, how to calculate the instantaneous rate? So, for instantaneous rate, what we should do is, suppose at any point, suppose at point P, suppose this is that point, suppose at point P we have to determine. So point P means it is at a particular time also. So at a particular point corresponds to given time, we are measuring it. What we should do mathematically is, we can go we can check this slope and we can go, we can extrapolate that line and can touch on both the sides of the graph. Suppose this is O, suppose this is A, and suppose this is B. And obviously this is x-axis and this is y-axis. Instantaneous rate is measured as this one, OA by OB. It's y by x actually. It is delta y by delta x. The slope we are going to measure. That means we are basically checking OA by OB, like that. So this is how instantaneous rate is experimentally measured. But this type of problem we will face less. Obviously it is there, but it is having lesser quantity as per our syllabus. So next topic will be the factors influencing the rate of the reaction. Let us see what are the factors on which it depends. Next one is the factors influencing the rate of the reaction. So let us see the factors. Factors influencing the rate of the reaction. So let us try to understand the factors one by one. So the most important factors are like this: concentration, temperature, nature of the reactants, presence of catalyst. So let me write down one by one. First is concentration of reactants. Next is temperature of the system. Temperature of the system. Third is the nature of reactants and products. Nature of reactants and products. Fourth is the presence of a catalyst. Fifth is surface area. And the sixth is exposure to radiation. Exposure to radiation. Now, there may be 6 factors, but it should be noted that all the factors may not be applicable everywhere. So let us see one by one now. So first thing first, let us see the concentration of a reactant. So first you write it down. Let us see the concentration of a reactants. Remember, there are mathematical expressions thereafter, but it may be noted that the rate is directly proportional to the concentration of reactants. That means if you increase the concentration of reactants, rate is going to increase. For an example, suppose we take this example, N2 plus 3H2 giving rise to 2NH3. Needless to say, suppose it was 1 mole, it is 1 mole. Now from 1 mole, if you are making it 10 mole, and this one also, needless to say that you will be getting more amount of NH3, because more amount of nitrogen and hydrogen will then react with each other to produce ammonia. So concentration of reactant is the obvious choice when we are talking about the factors. Then the next one. Next one is the temperature of the system. temperature. You need to understand that for every reaction, it is observed that for almost all chemical reactions, if you increase the temperature, the rate will increase. So if temperature increases, then rate also increases. Actually, behind this there is a logic. The logic is, if we are plotting energy versus extent of reaction, the reaction is normally like this: R giving rise to P. So this much we call activation energy. So for every reactant, if it needs to go to the product, it has to go through this process only, through this line. So you have to give this much of extra energy in order for a reactant to give rise to product. So if you give an EA is this EAct is proportional to temperature. So if you increase the temperature, obviously it will gain the required amount of activation energy and can go to the product very easily. Later on in this chapter, this will be discussed in much more details, but for the time being, only this much you can understand, that for every reaction to happen, there is a required amount of activation energy. If you give this that much amount of temperature, activation energy, the reactant can acquire and then it can go to the product easily. So normally what happens, with rising temperature, the reaction becomes faster, and the opposite thing happens when we reduce the temperature. Next is the nature. Nature of reactants. See, in the rate of the reactions, it is very much dependent on the reactants and the products. Remember, a chemical reaction involves the breaking of old bonds and the formation of new bonds. So therefore, easily the way the bond breaks and how easily the new bond will form, this will be the chemistry behind this. So it is not same everywhere. For an example, if I take 2NO plus O2, 2NO plus O2 giving rise to, here we can say 2NO2. And similarly, if I take 2CO plus O2 giving rise to 2CO2, both reaction looks absolutely similar, but unfortunately this reaction is faster while this reaction is slow. As I have told you, this bond may be easily broken and these bonds may be easily formed, whereas to break this bond, maybe, we are not going into details of this particular reaction, but maybe the amount of energy that is required will be higher, so this becomes slower. So as you can see, depending on the nature of reactants and the products, that means depends on breaking of old bonds and making of new bonds. So it depends on both of these. Okay. Then let us proceed for the next factor, which is the presence of catalyst. Next is the presence of catalyst. First of all, what is a catalyst? A catalyst is a substance which increases or decreases the rate of the reaction actually. But how it does so? Let us see. For that, we have to see this energy profile diagram. It is reaction coordinate on this side. It is the energy on this side. It is called reaction coordinate, as we have shown. This is R and this is P. And this is the way out. And this much is the activation energy. What happens is, in presence of catalyst, the reaction is having a tendency, carefully see, to find an alternative pathway to go for the product. This is called alternative pathway. And due to the presence of this alternative pathway, what happens? Now this becomes the EA. So obviously, here you can see the green EA is greater than the blue one. So here less energy is required. Catalyst is having some chemical nature, that is a different chapter altogether. But due to the presence of catalyst, what happens? It gives an alternative pathway. You see, this is called alternative pathway. And due to this alternative pathway, the EA, the activation energy, becomes less. So the reaction happens more quickly. So this is the reason why in presence of catalyst, the reaction rate differs. Next two are surface area and presence of exposure to the radiations. So in surface area, it is, I would say, in case of surface area, I am not writing it down. What happens is, larger the surface, suppose this board is the total surface area. So what happens is, if the reactants are present on this particular surface, one of the reactant is present on the surface, another reactant is present on the air. So then these two can interact at a much larger area. And suppose the surface area is less, for an example only this much, then what happens? The reactant is only exposed. Suppose two reactants, one is in air, one is in this surface. So this much of area is only the area of contact. So larger the surface area, the area of contact increases. And radiation is a completely different phenomena. For radiation, we have to go through that particular chapter only, but only one thing we can say: if it radiates, reaction becomes usually faster, or rather we can say, if due to radiation, it goes through completely a different pathway altogether. So in that case, prediction of the rate becomes comparatively difficult. Now, let us see the dependence of reaction rates on concentration. Next topic is dependence of reaction rate on concentration. Remember, whenever a chemical reaction proceeds, the reaction is getting converted to product. So as a result, the concentration of the reactant decreases and the concentration of the product will increase. So this is the general behavior. So let us see a graph between the two. Suppose it's a concentration versus time. So suppose R is giving rise to P. So with time what happens? With time, concentration of this decreases and here it increases. So as a result of that, what we can write is, suppose for reactant, if it starts from here, with time, it will be observed that it is decreased, like this. And of course, on the other side, the product will increase. The concentration of the product will increase, like this. What does it mean? Carefully see. Initially, the reactant concentration is high, and since the concentration is very high, the reaction will be faster, and the concentration drops down very quickly for the reactants. And for product also, initially it is very less, but the reaction rate will be higher initially, so it becomes very high initially. The product concentration increases very quickly. In this region you can see. And then it becomes a saturated value. Why saturated? Normally it is observed that most of the reactions are reversible. So reactant gives products, then product also gives reactant. So reactant does not become zero. And that is why the curve is like this. So we should be writing this one as increasing, this one rather, increasing concentration of products. Here we should be writing decreasing concentration of reactants, like that. So this is all about the dependence of reaction rates and concentrations. The next topic is, you can say, the introduction to the mathematical part. Although we have written the differential equation, but this is a very crucial way of writing the mathematical way of chemical kinetics. So this is called law of mass action. First of all, let us write down the law. The law suggests that at a given temperature, the rate of a chemical reaction is directly proportional to the product of molar concentration of reactants. So let me write it down first. At a given temperature, the rate of a chemical reaction is directly proportional to the product of the molar concentration of reactants. Product of molar concentration of reactants. By the way, this shorthand way of writing, better you don't do. I've got a habit of this. At higher level it is okay, but better you write concentration and temperature in full. So suppose for this one, what we can do is, suppose the reaction is like this. A plus B is giving rise to product. So according to this, we should be writing that the rate will be proportional to A into B, because these two are the molar concentration of reactants and we have written them in the product form. That means it is multiplied. So to remove this, we can write K into A into B. So this is how the law of mass action is written. A and B are the molar concentration of the reactants, and K, this one, is called the velocity constant or the rate constant to measure the reaction. So it is called the famous rate constant. Now what is a rate constant? Let us define rate constant. So for that, if I rewrite this, R is equal to K into B. So if this one is 1 and this one is 1, R is equal to K, right? So see, what we can say is, the rate constant, it is nothing but the rate of a reaction when the reactant concentrations are 1 or unity. So we can say the rate of the reaction, rate constant is, it is the rate of a reaction when reactant concentrations are unity. So this is all about the rate constant. Now let us see, looking at a value of K, what can we predict? So let us see that. So first you write it down, then we are going to see the characteristics of rate constant. Next is the characteristics of rate constant. First of all, rate constant of a reaction is a measure of the ratio of reactions. Means larger is the value, faster is the reaction. And obviously the different reactions will have different value of K. And remember, at a fixed temperature, the value of K is constant, and this is the characteristics of a reaction. And it is independent of concentration also for a particular reaction. So let us see one by one. First is, higher the value of K, you can say faster is the reaction. So higher the value of K, reaction will be faster. Second is, we should be saying that different reactions will have different values of K. Third one is, at a fixed temperature, the value of K is constant. And remember, this is the characteristics of the reaction. This is the characteristics. And the fourth one is, for a particular reaction, rate constant is independent of concentration. For a particular reaction, rate constant is independent of concentration. Check these two factors. It is different reactions will have different value of K, and a particular reaction, At a fixed temperature, this value is constant, and for a particular reaction, rate constant is independent of concentration. So this is all about the rate constant. Now, let us look into the rate law expression. So now, next topic is rate law expression. Because we need to know the terms carefully before we go into the numericals. Remember, to express the rate of a reaction as a function of concentration, it is essential to measure it experimentally. The actual dependence of concentration of the reaction species is the rate law of expression. For an example, so we can say it is the actual dependence of rate on concentration of reacting species. Suppose for an example, if we see that suppose a reaction I am writing, it is like 2NO2 plus F2 giving rise to, here it is 2NO2F. Now, as per the experimental observation, it is observed that R is equal to K into NO2 and F2. This is called the rate law or rate equation. You must be expecting there is a term 2. You must be expecting that this should be raised in power, but that doesn't happen here. Similarly, there are other cases also. Suppose the dissociation of N2O5. N2O5, what happens is dissociates into 4NO2 plus O2. Here also, if we look into the rate, it will be like R is equal to K into N2O5 only. This 2 will remain having no kind of effect on this. So it is, as I have told, it should be experimentally determined. The key essence of this particular thing is, it is the experimentally determined. Experimentally determined case, this one. Next is order of a reaction. Remember, the dependence of the reaction rates on concentration may be expressed in terms of the order of a reaction. And again, I am telling you, to calculate the order of a reaction, we must carry out the expression to find out the dependence of the reaction rate of individual reactor. That means it is an experimentally determined case. You have to carry a reaction experimentally, then only we can say. So suppose we have taken a reaction, say AA plus BB plus CC, giving rise to product. Now, as per the rate law, if we are talking about rate law, what we should write? The rate law will suggest that rate is equal to minus of dx dt, instantaneous rate if we are determining, it should be r into a, or you can write, without writing r also, you can write k into a into b into c. So what we have done over here is, we have just multiplied the reactants as we usually do, and their coefficients we are expecting to be raised in power as per the mathematical rule. This and this. Now, this one, that A, B and C actually isn't correct. In order to get the correct term, we are supposed to write rate is equal to K into A, B, C. They will be in multiplied form, true, but very carefully you see, the power of A will be P, for B it is Q, and for C it is R. Now you must be thinking, what is this R, P, Q and R? So let me write that P, Q and R, all these three are experimentally determined quantity. We have carried out this reaction and it has been found that the rate depends on A and its power should be P, not A. So it is experimentally determined value. And the order of a reaction is basically the sum of these values. So whenever we are trying to write the order, it should be in plus R, this one, not into P plus Q plus R. So this is how we determine the order. Again, this P, Q and R may be same in some of the cases, but usually it is not same. So usually these values are not same. So as we have seen, the rate law can be defined as the equation where the mathematical expression which denotes the rate of a reaction, where each reactant terms will be in the product form and each will be raised in power to some term. These terms may or may not be same to their molar coefficients. In this case it is not same. In very less cases they may be same. So each term will be raised in some power. The sum of that power is the order of a reaction. So in this case we can say it is nth order, and P, Q and R the experimentally determined quantity. It may or may not be same. Remember, P, Q, R and A, B, C may or may not be same. So to conclude with, we can say that suppose there is a reaction as AA plus BB giving rise to say CC and DD. So the rate usually should be like, as per the law of mass action, the law of mass action suggests that it should be A to the power A and B to the power B. But actually what happens, it is A to the power X and B to the power 1. Now this X and Y, as I was discussing, it is experimentally determined. And X and Y may not be A and B. So these two and these two may not be same. So this is the actual rate law expression. And what is the order of the reaction? If it is N, so it should be X plus Y. In this case it is called in order. When we will see problems, then that time it will be much more clear.